Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nobalkis binti Muhammad Shahrudin. Today my topic is design for sustainability of a short inner cable guide for Malaysia Aviation Group Boeing 7378 aircraft. The problem statement for this report are the existing Boeing 737 short inner cable guide is tasked with protecting critical cabin electrical wiring from vibration, impact, and heat. First one, vibration induced cracking at mounting point, excessive deformation from thermal degradation, broken mounting feature due to weak structural rigidity, sharp edge profile risk cable insulation damage. The environmental cost, replacing broken pipe without optimizing the design increase raw material usage, manufacturing emission, and non-recyclable end-of-life waste. For this project, have three phases. First phase is physical capture. Utilize 3D scanner to map the exact physical geometry of the worn legacy component, establishing precise interference dimension. Phase 2, point cloud generation. Transforming the scan into millions of special data points, isolating critical features like mounting hole and edge profile. Phase 3, CAD reconstruction. Rebuilding a flawless 3D data, this digital model serves as the baseline for structural optimization and sustainability upgrade, eliminating the need of design from zero. Objective for sustainable redesign. First, 6R integration. Apply acceptable reduce, reuse, recycle, recover, redesign, and remanufacture practice to the component. Service life extension. Eliminate weak point to drastically reduce the frequency of part replacement. Number three, environmental impact. Propose a sustainable manufacturing approach to lower net material usage and manage end of life effectively. Number four, quantitative validation. Utilize precise quality engineering method FMEA, RPN, calculation, material selection matrix to mathematically prove the redesign superiority over the legacy part. The methodology are Phase 1, failure identification and 3D scanning. Phase 2, point cloud generation and CAD reconstruction. Phase 3, 6R sustainable redesign. Phase 4, 3D printed prototype and fit validation. Phase 5, injection molding for final production. Phase 6, in-flight maintenance, tracking, and end-of-life management. The 6R transformation strategy. First, reduce optimize wall thickness and utilize the internal rib to lower mass without sacrificing strength. 2. Reuse. Repurpose the broken physical part as the definitive 3D scanning reference. 3. Redesign. Engineer stronger mounting point, larger fillet, and smooth edge to drastically extend service life. 4. Remanufacture. Capture maintenance failure data to continuously improve future digital illustration. 5. Recycle. Reproduce, reprocess, and off-life thermoplastic into non-critical product, aided by new material ID marking. 6. Recover. Implement control industrial energy recover when mechanical recycling is no longer viable. This anatomy of a sustainable redesign. First, optimize wall thickness, material concentrated strictly at high stress zone, thinned in a low load area. 2. Reinforcing rib structure, internal structural metric at high rigidity and prevent deformation without bulking thickening. Improve mounting bosses. Reforms screw support region with thicker pad to prevent installation cracking. Large fillet radius, rounded transition eliminate sharp corner, reducing stress concentration and crack intention. Smooth cable clearance, redesign routing pathway, eliminate abrasion risk for interior wiring. These are the reduce principle, visualizing mass efficiency through suitable engineering balance mass reduction with targeted structural reinforcement. By mapping material precisely to load path, the redesign achieved superior strength while shedding unnecessary weight. Matrix selection for short cable. Selection the cheapest material guarantee a linear waste trim, selecting PIC, polyether enter ketone, prioritizing operational longevity, flight safety, and reduced replacement frequency. As we can see, PIC have 5.4 strength to weight, 5.4 head resistant, 5.4 flame resistant potential, 5.4 fatigue resistant, and 5 point aerospace suitability. Weight score PIC 134. Device outperform ABS 72, nylon 94, and PEI 126. Physical validation, zero waste prototyping. To prevent the waste of expensive injection molding tooling on unverified design, physical validation was conducted via rapid 3D printing. Verification checkpoint. First, dimensional accuracy against surrounding cabin panel. Mounting alignment with existing airframe head hardpoint. Adequate clearance and smooth routing for electrical cable. Accessibility for aviation maintenance technician. Outcome: flawless physical integration confirmed prior to cutting final production molding. FMEA synthesize quantifying the risk reduction. Failure mode and effect analysis FMEA mathematically prove the efficiency for digital redesign and peak material selection. Before legacy risk, poor fitting accuracy, thermal degradation, mounting failure, critical 240 RPN. After design solution and result, negative 70% RPN, solved via precise 3D scanning and 3D reconstruction. Negative 66.7% RPN, solved via integration of aerospace grid peak. Risk eliminate, addressed entirely by reinforced bosses and optimized fillet radius. The sustainable production, discovery and digital twin, legacy part retrieval, failure analysis, 3D scan, and CAD reconstruction. Second, validation, 6R digital optimization, 3D printed prototype, aircraft fit verification. 3. Deployment, injection molding, PEEK, aircraft installation, maintenance tracking loop. The workflow ensures dimensional stability and repeatability while establishing a closed loop system for continuous feature engineering improvement. End of life management for this part. Stability require planned obsolescence path. The new shroud inner cable guide is engineered for clean disassembly using standard aviation tool, no permanent adhesive. Step 1. Sorting. Accelerate by embedded material identification marking. Part A. Mechanical recycling. Proceed into granule for non-critical industrial application. Path B. Control recovery. Industrial energy recovery utilized in the material is to degrade. Path C. Landfill. Last resort disposal drastically minimized by the new extended lifespan. The environmental operational divided. Extended life cycle by eliminating stress, construction, and utilizing peak. Part longevity is drastically increased, cutting replacement demand and raw material extraction. Lightweight efficiency, optimized mass distribution strip 10% of the material weight, stability by continually contributing to reduce aircraft drag and fuel consumption. Zero waste irritation, shifting trial and error out of the physical realm, injection mold, into the digital realm, CAD and 3D printing, eliminate deployment waste. For the conclusion, the transformation the Boeing 737-8 short in a cable guide has been successful, transformed from a legacy liability into an optimized sustainability asset. The six are proved by integrating reduce, reuse, recycle, recover, redesign, and remanufacture. We engineered and a part with stronger mounting, optimized mass, and a drastically lower FMEA risk profile. The core takeaway through engineering suitability is not merely recycling garbage at the end of product life. It is a result of rigorous data-driven design decision made at the very beginning, ensure product endure longer, perform safely, and respect environmental limits.